My name's Tom Dick. I'm a mathematics professor and also a math advisor for Texas Instruments. This video is part of the TI-Focus AP Calculus series. We're going to use the list feature on the TI-84 to work on a couple of BC topics. Euler's method applied to parametric motion in the plane. To get started, we're going to go to the statistics editor, and here you'll see that I've already entered the table of values that were presented in this problem. Column 1 here with time, these are selected time values for t, and the second column are the corresponding y prime values for the y coordinate of the position. Now we're going to use these other three lists, L1, L2, and L3, to build on Euler's method. Now we're told that at time t equal 12, the position or y position of the particle is -3. So let's go ahead and enter those values in L1 and L2. Now we're going to use Euler's method, and so we're going to work our way back to time t equal 4 in steps of 2. So at time t equal 12, we know that the y prime value is -5. I'm going to multiply that by our step value, which is -2 since we're going backwards. So -5 times -2, and I'm going to enter that into L3. Now that's the increment that we'll use to estimate what the y position is at time t equal 10. So I've entered t equal 10 in L1, and we were at -3, so let's take -3 and add on this increment of 10, because that's the difference that we're estimating using the derivative value at t equal 12. So -3 plus 10, and now we are estimating that we'll be at y position 7 at time t equal 10. And now we keep working in the subsequent steps. Okay, at t equal 10 our y prime values -1. We'll multiply that times the step size. Again, this is -2. That product will enter into L3, and this is what we'll add on to our y position at time t equal 10 to get the time position estimate at t equal 8. So at t equal 8, we'll take our previous y value, 7, add on this increment 2, and we get 9. And we just keep on working in this manner. Our y derivative at t equal 8 is 3. We'll multiply by our step size of -2. That gives us our increment of -6. So at time t equals 6, we're estimating that we'll be at a position of 9 plus -6. So I'll add 9 and -6, and that'll give us our estimate of our position at time t equals 6. We've got one more step to go. At time t equals 6, our y prime value is -2. So let's enter that value of -2. And our step size will multiply by, which is also -2. And that's giving us a product of +4. And so our final estimate for where our y position will be at time t equal 4 will be that previous position of 3 plus that last increment that we calculated, 4, for a result of 7. So this is what we're coming up with as our Euler's method estimate of the y position of the particle at time t equal 4. In the same problem, we're given the x-coordinate at time t equal 12 is 4, and we're explicitly given x prime of t. So we're going to use the fundamental theorem of calculus to get the exact position of x of 4. So we're going to integrate from 12 to 4 of the explicit formula for x prime of t, which was given to us as t over the square root of t squared plus 25. And that entire quantity is under the square root sign. So I've got my t squared plus 25. And now we'll integrate with respect to t. And see what our final result is. See what we get as the x-coordinate of the position at time t equal 4. There it is. And now let's compare to what we would have gotten if we'd used antiderivatives to calculate a definite integral. Time t equal 12 we have 4. Because the lower limit of integration is larger than the upper, I'm going to reverse and subtract. And our antiderivative is just the square root of t squared plus 25. So I evaluate that at t equal 12. That gives me 13. Minus evaluated at 4, which is square root of 41. And when all the calculations are done, we see we get exactly the same result. And that's reassuring. Well, that winds up this short video. For more resources like these, please see education.ti.com.